Hello students, last class we discussed about the various formulation for work done. For example, first of all we studied about the work done, which was the formula derived was Fs cos of theta. Then we said, and we had a discussion about that work done is equivalent to energy. So energy or work done, they are same, that is why their SI units are also similar. So various forms of energy were, which we discussed as per formula. One was potential energy, that is the energy possessed by a body by virtue of its position. So the formula was mgh, and in another case the energy possessed by a body by virtue of its motion, that was kinetic energy. So kinetic energy is half mv square. Let's try out some numericals, but before that we are going to devise one more relation between work and kinetic energy, and the relation is famously known as work energy theorem. So we'll start with this topic today, work energy theorem. Now this theorem states that work done is equal to change in kinetic energy. So in general, if I say that there is this body of mass m which was initially moving with velocity u, and after covering some distance due to application of some force F newtons, the body is finally moving with velocity v. So whatever work has been performed on this body, that is work done, this is equal to change in kinetic energy. Delta is a symbol which represents the value change. So change in kinetic energy basically means final kinetic energy minus initial kinetic energy. See, it's a simple concept. For example, your weight is currently 60 kg and after 2 months it's 80 kg. So the change in weight is 80 minus 60, which is 20. So that is how we always formulate the value of change, which is final minus initial. So this is kinetic energy final minus kinetic energy initial. Let's try to make this relation valid. Let's try to prove it up. First of all, we'll start with left hand side, which is force, right? No, this is not force, this is work done. So let's start with work done. Work is force times displacement. There is a involvement of angle as well, which is cos theta, but in this case, for the case of simplification, I have taken the direction of force and initial velocity in the same direction, so we don't have to consider the angle yet. Now work is force into displacement. Force is mass times acceleration into displacement. Now either I have to put the value of A or S from already known equations of motion into this equation. So what are the equations which we know? We have V is equal to U plus AT, S is equal to UT plus half AT square. So regardless anything, we are going to reject these two equations because we do not have the value of time per se. So we are going to use the third equation, which is V square minus U square is equal to 2AS. So I can either take out the value of A or S or both here. So I am taking the value of both here. This equation is giving me V square minus U square over 2, this is equal to A into S. So instead of this A into S, I am putting V square minus U square over 2. So I am left with this thing, M V square minus U square over 2. So this thing becomes M V square over 2 minus M U square over 2. Or I can either write it as half M V square minus half M U square. Now when the body was moving with initial velocity u, the kinetic energy, which is kinetic energy initial, is half M U square, and when the body is finally moving with the velocity of v, the final kinetic energy b, kinetic energy F, is half M V square. So now you see that final kinetic energy minus initial kinetic energy is half mv square minus half mu square, which we have already deduced. So this is basically change in kinetic energy. So what we did, we just tried to evaluate the value of work done and we reached the point which is change in kinetic energy. This proves the statement that work energy theorem exists. So in general, the statement would be work done is equivalent to change in kinetic energy.